So we are going to talk about the solutions of the equation of transfer in the stellar atmosphere. So I had discussed about this in our previous video of the radiative transfer, I mean the derivation of the equation of transfer. In this particular video we are going to discuss about the solutions, that what are the different simple solutions for not generally the reality but for the close approximations to the reality. That's why we are going to discuss about the Eddington's approximations of the equation of transfer, which is called the gray body atmosphere. So this is the topic of our video we are going to discuss about. So first of all, let me write out that what was the equation of transfer. So the equation of transfer was exactly the derivative of the radiation. Here there is mu and it is equals to the minus. So this was the equation of transfer I had arrived, but there is a thing that this was not the exact one. What I have derived is that it also contains what is called the scattering phenomena also. This is under the simple assumptions, and under the simple assumptions you can get this particular radiation transfer. And what are that simple assumptions? So that are going to be the, first of all, plane atmosphere. This was our first assumptions, that it has to be the plane atmosphere, and second was the local thermodynamics equilibrium. So these are some of the conditions that should hold while deriving this particular type of the equation of transfer. This is like the simple type of the equation of transfer, not a very complex one. So this is the thing. So now what we are going to next is that we are going to find what are the solutions of it and what is the actual problem. So for this we have to discuss about the first solution, which was by the Eddington's solution. So this is the Eddington's solution. So let's discuss about this particular thing. Okay, so in Eddington solutions, what we're going to do is that in our equation of transfer generally this particular absorption coefficient is dependent, but in the Eddington's solution it is constant. It is treated as a constant, not as dependent on the frequency and all that stuff. It is a constant under the Eddington's solutions. And what our main aim is in the Eddington solutions is to find the relation between the temperature and the optical depth inside the star. Optical depth. So we are going to find what is the relation between the temperature and the optical depth inside the star, and this is our main aim to find out. So this is a thing for the Eddington's solutions, and where this particular absorption coefficient is constant, this is called as the gray body approximation, or you can say gray body atmosphere. This is far from being the reality, but still we do and study about this because it can help us in finding some of the complicated solutions. It's like a warm-up exercise for the different other types of the solutions. Like one is from the Chandrasekhar, which is the accurate descriptions for the, like you can say, for the photosphere area, not for the inside. Okay, so this is our Eddington solutions, and we are going to derive the relationship between the temperature and this particular optical depth. So how we're going to do this? So for this, first of all, our assumption is this, our absorption coefficient is constant, and the second thing is that what we're going to do is that defining the optical depth. So optical depth is defined as in the general sense, the optical depth is generally an alternative for the geometrical depth, because optical depth is somehow very easy in doing the calculations than the geometrical depth in the stellar atmosphere. So it is equals to the integral of the absorption coefficient plus the scattering coefficient, and here is rho and here is dz, where dz is our actual geometric distance. It is not the sum of like optical depth, it's really the geometrical distance, and here is our optical depth. So this is the thing we define, and that rho is of course the density. So in our case, we have assumed that there is a local thermodynamics equilibrium. So for the Eddington's solutions, what we're going to do is that we're going to put this particular scattering coefficient as 0, and this is equals to nothing as an integral of kv and dz. And if you write it in the differential of that particular, and here should be true. Okay, so if a differential of this particular optical depth, then this can be written as d tau is equals to the k rho dz. So in Eddington's approximation, this is how we wrote the optical depth differential. And also this is very, very important. It's not always true. It's only true in the gray body atmosphere or in the Eddington's approximations. So this is the thing. Now what we're going to do is that we're going to find out that what is called the mean intensity. Of course, it is the intensity in all over direction, in all over the solid angle, and all of that particular frequency, and it is represented as the integral from 0 to infinity over all of this particular frequency, where mu, this is the sign of the indices for the frequency. And same we define the source function, which is equals to the integral from 0 to infinity, 0 to infinity. This is not exactly the source function. Why I am telling this particular quantity as source function, you will get it, and over all frequency. So this particular is called the Planck's function. But why I'm calling this source function? Because see, here in this case of the black body assumptions, I have defined this source function. So first of all, you have to know that how exactly we define the source function to know that why I'm calling this as source function, even if it's a Planck function. So to know this, you have to know that what exactly is the source function. So let me tell you about that. Source function is defined as the emission coefficient divided by the absorption coefficient plus the scattering coefficient. This is how we define the source function. It's just like the ratio of the emission coefficient divided by the scattering coefficient plus the absorption coefficient. This is J, okay? But here in this case, in our Eddington's approximations, this scattering coefficient is 0. So there is no, you can say, any generality that the radiation is scattered in the stellar atmosphere. So you will see that this is equals to the ratio of emission coefficient to the absorption coefficient. Now remember carefully that I have defined a condition called the local thermodynamics equilibrium. What does that mean? So if you have studied the black body radiation, it holds the thermodynamic equilibrium, and we write our this particular emission coefficient as some absorption coefficient multiplied by some sort of function we define in the black body radiation. You have to watch some of the videos on the black body radiation to know about this. So this is how we define the Planck's function. So if this is how we define the Planck function, and if local thermodynamics equilibrium is holding in our conditions of the Eddington's solutions, then this must be true that this particular Planck function is represented as the ratio of the emission coefficient to the absorption coefficient, and this is exactly what is called the source function here in this particular case. So yet it is true. That's why here I was calling this particular Planck function as the source function, because it is equal in the case of the Eddington's approximations. So I hope all of you get the point at what I was trying to tell. This is why I told the source function, this particular Planck function, as the source function. So this is the case here. And another case is that this mean intensity is also equals to this source, what this is called, Planck function. You will say, why this is equal? So you have to know another concept called the radiative equilibrium. This is also a very important point in discussing about some of the simple solutions. So radiative equilibrium, what is the meaning of this? The meaning of this is that suppose that there is some sort of cylindrical surface. So radiative equilibrium is that the amount of radiation that entered and the amount of radiation that is gone from this particular cylinder should be equal, okay? And that is the meaning of the radiative equilibrium. And that is also what holds in these particular solutions of the Eddington's approximations. And using this, you can generally prove that this particular mean intensity is equals to the Planck's function. I hope you're getting the point that what I was trying to tell. So this is how we define it. Now the next step is to define a simple relation. So if you do some sort of mathematics, some solving differential equations, what you will get is that what is the relation between the intensity and the 3 by 1 minute. So intensity and this particular flux F. Now you will say what that particular F is and how you find this particular thing. So here should be 4. Okay. What is here F? You should know what is here F, and I will discuss it. How you generally determine the temperature of a sun? Suppose that this is the sun, and how you will determine the temperature? You use the concept in the black body radiation, that the power radiated is equals to the sigma multiplied by T to the power 4. Okay, so that's how this particular, there is another way of defining this. There is another way of defining the power, which is the pi multiplied by F, where F is the radiant flux. You have studied the electrostatics in the Gauss law about the electric flux. So that's the same thing here. It is a radiant flux, and it is also equals to this. This is sigma T to the power T to the power 4 here, and this is the same thing. So this is another alter, and F is the radiant flux. You have to know this is called the radiant flux. So here, what is the meaning of T effective? So T effective generally you can say is the temperature of the photosphere, you can say the outer surface of the sun. And what we have to find is that we don't have to find this particular temperature effective. We have to find the temperature at any point inside of the sun, and this is our main motto, and this is what we are gonna do. So this is the relation between the mean intensity, optical depth, and this particular F. And if you will integrate and find the mean intensity, it is equals to the 3 by 4 F tau plus some sort of constant, which you will find using the boundary condition as 1 by half F. And if you take common, you will get I as 1 by half F 3 by 2 tau, just taking common 1 by half F. And this is the result for the mean intensity. So this is how we define this. Now what our main motto is that we have to find a temperature inside the sun. This is our main motto, and its relation with the optical depth, as I had said before. This is our main motto. How are we going to do this? So we're going to define two things. First of all, we are going to define that pi, see this very carefully, pi integral of v from 0 to infinity of this particular function is equals to sigma T to the power 4. Now this is a more general version. Let me write it clearly. That pi b integral from 0 to infinity of t is equals to sigma T to the power 4. There is a difference between this temperature and this temperature. Is here this particular temperature T is the effective temperature, which is using the black body approximation, and here this particular temperature T corresponds to the temperature inside the sun, more general way, not only on the surface. That's why we integrate this Planck function to get our temperature at any point. So if this is the case, how we are going to define the relation between the temperature and the optical depth? So this is our, let's say, some equation. Let's say it's equation number 1. Let's see some another equation. Of course, pi f is equals to the sigma T effective. What I will do is that let me see that where I can do some sorts of substitutions to find the result. Okay, so I can write T effective. 1 minute. Let me. Okay, so this is the case. So we are going to do some manipulations to find out. Yes, here I can do is that pi v is equals to sigma T to the power 4. I can write T to the power 4 as pi by sigma, and if I substitute the b, because I is essentially equals to the b, so b and I are same, so you can just put the formula of the mean intensity and b, this is same, so it is equals to the f by 2 3 by 2 tau plus 1. So this is the formula. So this is, now what I want to do is that I want to find some more general expression. What do you mean in general? I mean I want to include this effective temperature also. So this is the case, then T to the power 4 is equals to, if I will substitute it back, and if I put here F as sigma T effective to the power 4 divided by pi, put it here, then sigma and sigma will pi and pi will cut out. It will eventually become 1 by half 3 by 2 tau plus 1 and T effective to the power 4. So this is the expression that I want to find out. The relation between the general temperature, the optical depth, and here also is the effective temperature. Here effective temperature is constant, of course. It is equals to the temperature at the surface of the star, which is, I guess, 5972 Kelvin something. I don't remember actually what is. So this is, I guess, the thing. So now we have derived the relationship between the temperature and the optical depth. So now we do some sorts of important conclusions from it. So what is the point where you can say this T effective equals to the temperature? What is that? Is the optical depth. What's the optical depth at which this is true? So this is the thing I'm gonna find out. So let's do, and it's obvious that the only thing, that only reason it to be true is that 3 by 2 tau plus 1 should be equals to 2 in order to get these two quantities whole should equals to be inequality. So it is like the tau should be equals to 2 by 3, and this is a very important thing. Anybody can ask you that, so this is very important thing. In Eddington's approximations, at the optical depth of 2 by 3, the effective temperature, let me write it clearly, the effective temperature is equals to the temperature. And this is a very, very important point that you should remember. So this was our main motto, actually finding this relationship between the temperature and the optical depth, also the effective temperature. So this is a very important point that you should remember. So this was the solutions on the Eddington's approximations. One more thing is that we have generally, okay, so this particular equation, so there is a solution of this particular equation also, and I'm going to mention it in the next video after solving this particular equation. So here our main motto was the relationship between the temperature and this particular optical depth, but one another important thing is that you have to solve this particular equation to get the temperature dependence on to get the intensity dependence on all of that particular, on solving this differential equation, which is not very hard. It's a medium level differential equation. You can also try and you will solve this. Okay, so this was the today's video on the radiation transfer.